or my talk, rather, LLMs will not replace automated keyword extraction. So I'm Kimberley Huizing. We just had a small introduction. So indeed, I generally work in Scala. I was working in different software companies, always building some kind of a data pipeline in Scala that needs to be robust, low latency, high throughput. But since October, I am working as a software development consultant at a company called Cebia. So now I work in whatever language the client works in, which is generally not as nice, unfortunately. Yeah. So, but I'm extra happy to be here today and get into the functional programming a bit because it's much better than the mainstream languages that I unfortunately work in now. So, my talk, LLMs will not replace automated keyword extraction. Let's go a little bit into why did I pitch this talk. So first off, LLMs are very popular right now. Everybody uses it for everything. It's the shiny new thing. I'm a little bit of a skeptic. I feel like it's a little bit overhyped. Like we do a lot of knowledge sharing at my employer, Cebia. Everybody's always building like hobby projects in LLMs now, and that's everything everybody wants to talk about. I think LLMs are great, but I do think they have their use, and actually older techniques also still have their use. At the same time, I also wanted to build something in Clojure. Yeah, yes, Jordan. That was very appropriate because I got lured into Clojure through the community. Yeah, Scala, I love Scala. I am mourning its slow decline. It's a beautiful language. There's less and less work in it, unfortunately. And I have done a lot of work in Scala. I know Scala very well, very intimately. So I'm just shopping around a little bit, and Jordan took advantage of that. No. But the Clojure community is great. Like they're honestly great. They're very like cohesive. They're very nice people, and it just got me very curious about it. It's also a functional programming language on the JVM, which I have good experiences with. So why not? And then if you're gonna build something in Clojure, it's a Lisp. So it makes sense to do some kind of Lisp processing, right? So yeah, I felt like this was a good use case for it. And then finally, I don't know if you have ever heard of hyperlexia. It's a thing. It's like the opposite of dyslexia. So I didn't know it was a thing until a couple years ago when I happened to read something about it and realized like, oh, I was not just a strange child. This is actually a thing. Like some kids have that. It's something that occurs in children because, by definition, because it means that you have language capabilities beyond your years. So I never did baby talk. I immediately spoke in like fully qualified sentences, basic sentences, but like grammatically correct ones before my second birthday. It kind of freaked people out. Yeah, because like I'm not a tall person. I was a tiny child. I had the voice box of a toddler, but I was speaking like an adult. Like people would like stop my mom in the street and be like, how old is this child? Yeah, and I was obsessed with like letters, numbers, words. Like even as a toddler, I wanted to play with toys that had some kind of representation of numbers and letters. And that kind of stuck with me into adulthood. I love things like regex, logs, language processing. So yeah, that's how I came to this subject. So what is automated keyword extraction? It is what it sounds like. It's a technique to extract keywords from a document. So I made this little graphic. Can you believe I made it? Yes, you can, because it's shite. So this is how it works. So yeah, automated keyword extraction algorithms fall under the umbrella of natural language processing, which is a subset of AI. So it's an older kind of technique. It's more rule-based. It's unsupervised. So supervised techniques, supervised approaches are where you have a training cycle, where you train the thing then it's supervised. And it's called that because it's like supervised learning. It's kind of a similar way that a child learns from a parent or a student learns from a teacher. In that same way, the AI learns from the person who trains it. Unsupervised approach, on the other hand, does not have this cycle. It just does whatever you tell it to do. The algorithm, the programming, does what it does. No more, no less. There's no training. So what automated keyword extraction does, it does analysis of whatever text you feed it. It gets some statistical features from that, and then it uses those statistical features to determine what are actually like the most important words in this specific text. So first, you need to tokenize and segment a text. So you've probably heard of tokens in the context of LLMs. So a token, you can think of it more or less like a word. It's a little bit more complicated than that because, for instance, if you have a possessive and you have a word or a name and then apostrophe S, it still needs to stick together. You may have things like notations of molecules where you have like a mix of characters, also needs to stick together. So it is a little bit more advanced than like just a word, but it's kind of, you can think of it like words. So you need to like split it up into words. You also need to segment, which is knowing where the sentences start and end, because that also is necessary so that the algorithm has the context. Like knowing what is a sentence is very important to know the context. And then there are certain weighted factors which vary per algorithm. So there are several ones available. There's TF, IDF. There you feed it a collection of documents, a corpus of documents, and then it's going to see like, oh, which words are more prevalent in this one document than they are in the entirety of the corpus. If they are more prevalent in this text, they're probably important. Then there is RAKE, which is Rapid Automated Keyword Extraction, and that one only uses one document. You can just feed it one document, it's enough. It just does analysis of the words in this document, takes its statistical features, and bases importance on that. Then there's YAKE, which is yet another keyword extraction. It's, it's like RAKE, but a little bit more advanced. It has like a little bit more logic. So this is the one I picked for my project. And there's also TextRank, which uses grammar, and it takes like a sliding window of a document. So as an example, I took the Lambda Days website. So this was around December. So there was not a lot of information on there at that time. There was just one page that had some information about, this is the text, basically, or part of the text. It was mostly about high level, like what is the conference, what is its missions, mention of early bird tickets, and most of the information on there was about the call for papers. So I fed that into the YAKE algorithm, and these were the keywords. So as you can see, it's pretty good. Like it does recognize that Lambda and Days should stick together, that has some kind of meaning. It doesn't know what is the meaning, but it knows that these two words together mean more in this specific text than they do when they are separate. And the same for functional programming worlds, worlds of academia, etc. You can see it did a pretty good job.
Yes, please.
So, for the title of my talk, I needed a hook, right? So, let's do a small comparison. LLMs obviously have a very wide range of use cases, and they also generate language. Like you can ask it anything, you can talk to it like a person. At the same time, they do sometimes make mistakes. We all know this, right? We've heard of hallucinations. It's also biased by the training data. So YAKE and the other automated keyword extraction algorithms, on the other hand, are very scoped. They do exactly what you tell it to do, no more, no less, but they are also very precise. And they are very lightweight. Like you don't need a ton of computing power. I just use this tiny library, ran it locally. It's done in within a fraction of a second. It's very lightweight. So there are certain use cases where you might still want to use automated keyword extraction. Maybe you have some kind of a company or brand and you have a ton of blog posts and you want to do search engine optimization. Then you can just like get the keywords for every document. Or maybe you're in humanities and you want to do some kind of research on a giant body of articles. You want to do like an analysis of discourse or something language-based. That might also be a use case for it. So the use cases are much more niche, but there are still use cases for it. And in those cases, it will be a better choice than LLM. All right, now to go into the implementation bit. So I found this library, which is referenced on the first line. It was in Python, unfortunately, because yeah, a lot of data, AI, NLP stuff is built in Python, obviously. So that was the one that I found. And then I was going to build it in Clojure. So I am not very familiar in Python. I avoided like the plague. I had also, so I had also never used Clojure. So I pitched a talk to build something from a language I'd never use in a different language I never use. Great idea. What could go wrong? So yeah, when I pitched it, I had 6 months' time. In the end, some circumstances happened. I ended up not having nearly as much time as I thought I would. So I didn't meet my goal, which my goal was to implement all of the features from the YAKE library, get the same results in my custom Clojure implementation. Did not reach that goal. So in reality, I spent most of my time implementing the tokenization and segmentation. So this example library uses a different Python library, which is called segtalk. And of course, I could not use this library in Clojure. I also didn't want to look for an alternative in Clojure because this is like the first step in the automated keyword extraction, and it is core to its functionality. So if I use a different library and the implementation is slightly different, I've introduced a variable that is going to mess with me. I will never be able to debug it. So I figured I just need to rebuild this other library as well, or at least the bits of it that are used in the YAKE library. And that is where I was at when time ran out. So I did build the tokenization, or at least the features of it that are used by the YAKE library. I also have tests for those that work. So that bit is fully done and yeah, works. Happy with it. Segmentation almost done. And after that's done, like the rest of the YAKE implementation will be like 1.5 days. But yeah, I did have a lot of learnings already. I did do a lot of stuff. It will be interesting to talk about, I think. I hope you guys will agree. So first off, we already kind of discussed what is tokenization, get the words, segmentation, get the sentences. All right, remember that? So here are some of my test cases to illustrate it a little bit. Don't worry, you don't need to read the whole thing. So the first test is like the step before the tokenization. It's basically like a regex to split the sentence, and then the second test case tests the actual tokenization, which is slightly more refined. So if you look at the first line and compare both, you see at the top, the first one, what you see is a sequence, and that is the expected result. At the end of the line, you see the input, and you see at the end, it still has sentence and a period grouped together. If we go to the second one, after the tokenization, so the first one just tests the regex like separately, then the second one is actually tokenized. So the period is split off of the word sentence. It is not discarded because we need the period to know where the sentence ended. And we also need to know that this period is a separate token from the word. So it's not, for instance, if there's an abbreviation like I period E period, it would keep them together because that is one token. But this is a sentence ending period, that is a separate token.
Oh, damn it.
So this is a little bit of a surprise that I ran into. So in the Python bit, like the left is Python, you see the bit that I marked, that does the thing of the first test case. So it's splitting the text. And yeah, I think a lot of you will probably be familiar with the split implementation in JVM languages. You give it a regex, and then it, based on that regex, is going to split the text. It will give you what occurs before, what occurs after. So in this case, the Python implementation was also still keeping the match. And unfortunately, I couldn't get it to do that in the JVM implementation. Like the regex engines are different. So I needed to build something custom for that. So that is the Clojure bit on the right side. So I recursively go through the string. I match based on the regex. I check, was there something preceding the match? If so, put both of them in the list. If not, then just put the match in the list, go through until you reach the end of the string, return.
So now, let me know score.
So this is the regex. Yeah, I know. So on the left is Python. This is actually the regex. So what they did, they had some kind of a verbose mode. So they made it with like all kinds of comments in between and like white space. And then at the end, they feed it like some variables that is going to replace in the string. So I had to like manually like get that into regex. So on the right is the giant regex that is used for the tokenization. That is one pattern. So something else I run into all the time is the flow control, of course, very different in Python and in Clojure. I kept, like the Python code was littered with all of these like if else, and like loops everywhere, like old-fashioned loops with indexes. And then there's all over the place, you have breaks, you have passes, you have yields, you have returns. So I don't know if you will notice, but in Python, a yield does not break you out of the loop. You yield something, but you continue, which always baffled me. So there's like, I don't know, it's meant to be readable. I understand that it is more readable if it's like your first experience programming, but personally I find it confusing because you have to go through all the time and be like, where could I revisit here? Could I not? I don't know. I don't find it clear. So in Clojure, just use recursion and immutability. I like it. It's the better way. So here's a little bit of a comparison of what I just mentioned. So here we have the Python code from the example library. And then on the right, I implemented the same thing in Clojure. So in this case, the Python one actually wasn't too bad. There were ones that were like monstrosities, but they would not be readable on the slide. But yeah, this is a little bit, gives you a little bit of an idea of what I just referenced. I'll give you a few more seconds. All right, so how did I like working in Clojure? The rapid prototyping, really enjoyed that. That is something I read about beforehand. Like if you ask ChatGPT, like what are like defining features of Clojure? If you ask people who work in Clojure, rapid prototyping is something that comes up a lot. So I was a little bit primed, but even if I wasn't primed at all, if I never heard anyone say that, I would still have come up with that because it was very quick and easy to get started. Just build a little bit of code, build some test cases, go iteratively. I know I was supposed to use the REPL. I will do that next time. I'm sorry, time constraints, guys. Yeah. I did start to use Emacs though. Like I was learning Emacs, I was learning Clojure, I was doing the Python, like all of it, yeah. But I liked it. The purity of it, beautiful, enjoy that, feels like math. I also like the uniformity, like the vision behind it. I like the abstractions over the collections, which reminds me a lot of like the type level stuff in Scala. In some cases, I was a little bit annoyed that it was so bare-boned. For instance, regex, if you work with regex in Scala, it's like a dream. It's amazing. You have all the information that you have on the regex match in the Java API, but you also have the pattern matching and all of the good stuff that Scala gives you. Beautiful. Clojure is a lot more primitive. Didn't like it as much for regex specifically. The sum function as well is one of those things. Like at some point it was the best performing way to get the first item in a collection that matches whatever you're looking for, but then it returns a Boolean. So then you still need to write a little bit of code around it to actually also retain whatever the list element was, because I'm not interested in a Boolean, I'm interested in a list item. So in Scala, you have out-of-the-box functions for that kind of stuff. That was a little bit different. So there were like small like annoyances like that. But overall, I had a very good experience using Clojure. I definitely think I will use it again. Here's a little bonus slide. So I went to the Wikipedia pages of Clojure and Python, and I did automated keyword extraction on the Wikipedia pages. I thought that would be fun. I think it gives you a little bit of an impression of the community. We see a lot of mention of Rich Hickey on the left. We see just a lot of the word Python on the right. So yeah, I thought that was an interesting culture check. And again, an example of how you can use automated keyword extraction. And with that, we're straight on time. No time for questions, but I'll be around. And also, you can find me on LinkedIn.